Logarithmic functions, usually when I say log here, students have something different in mind, but in junior high, they also think of something different there too. So logarithmic functions. So this slide is telling us what a logarithm is, and some students get really confused by what they're looking at right here. But really, this goes back to what we've been talking about earlier on in the course, is that when you look at a math problem, sometimes you want to change it into what you want it to be, right? Like, you can look at something like x, you could say x equals 3, and that's a true statement right there. We just said x equals 3, okay. X can equal 3 if you want it to be. But what if you wanted it to be 1x? See if I can, that's a 1 right there. Let's say you wanted that to be 1x. Is that okay? Yeah.
Should be.
I actually didn't change the overall value of that equation right there. And that's okay that we can do that, right? In fact, if I wanted to do this and change that expression, that equation into, let's say, 2x's minus an x, and I said this equals 3, I have not changed the overall value of this equation. I just changed the way that it looks. That's all I did. We've seen that when we're solving equations, right? So if you had something like, 3x plus old 9er equals maybe 18 right here. If you were to solve this equation right here, you would eventually end up with x equals 3. And x equals 3 would make this equation true. But again, you didn't want the equation to look like this. You used principles of equality to narrow it down into something that looks a little bit easier on the eyes, hopefully. 1x equals 3. Now, I kind of went backwards here and said, well, let's change this into something that's more ugly. Fair enough. Maybe that's what you feel like logarithms are. So logarithms, what I'm trying to say here, because this is all linear crap, logarithms are based off of exponentials. Okay, so if you look at an exponential equation, I'm going to work here at the bottom, you have a base, and the base is raised to a power of x. Okay, so this goes back to terminology for exponents. B is what we call a base, and then x right here is the exponent, or power. And this would read b to the power of x. Okay, now this equals some value. Let's just make it, I don't know, y. Just so we have an x and y. Y is what we would consider the product. Now, if you're familiar with the word product, that's on purpose because bases and exponents represent repeated multiplication. So if you took this repeated multiplication problem, it could equal some value. For example, as an exponent, we can say 2 to the power of 3 equals 8. And that's a true statement right there, 2, 4, 8. You have a base of 2, an exponent of 3, and a product of 8. What a logarithm does is it takes this exponential equation and changes the format of it. Now again, do you feel like it's changing it for the better or the worse? I don't know. You get to decide. But the logarithm, so log, I'll usually make it the L kind of cursive like that and lowercase letters like this. The B right there for your log is the base of your exponential equation, which in this case is 2, right? So it's log, that reads log base 2 of whatever the product is. So over here, where 8 is the product, it's log base 2 of 8. And you notice that we write the base a little smaller, kind of like we would with an exponent. And then the product is also bigger, but it comes after the base. So this is the way that logarithms are shown. It would equal, though, it equals the exponent, which in this case was 3. So 3 equals log base 2 of 8 is exactly the same thing as 2 to the power of 3 equals 8. If you wanted to, for some reason, just to jack people up, you could be like, hey, this is 2 to the power of 3 equals 8. And they can't argue with that. It's true. It's just written in a logarithmic format. So what we end up doing here is we get to say, you can go between these two formats if you want to. Maybe exponential form is better. Maybe the logarithmic form is better. I don't know. You have to decide. And there are ways to tell, of course, depending on which values are missing, because here we have all three values. You got a base, you got an exponent, you got a product. Sometimes the base is missing. Sometimes the exponent's missing. Maybe it's the product. I don't know. Sometimes it'll be written in this format. Maybe it's good to see it in both formats so you can see which one is best and easiest to solve, because if you can, then you can solve it hopefully a little bit quicker. All right, write the equation in logarithmic form. Assume that all constants are positive and not equal to 1. This last sentence right here is just the formality. Ignore it. Okay, don't worry about that crap. All we're saying is just please change this format into logarithmic format. So I'm going to take, let's do that, yeah? Okay, so I'm going to take my log. Here's a log. My lowercase g's can look like y's, but that's an okay g for me. And then, look, it's base 5, right? Now remember, the vocabulary for exponents is crucial. Right? You got bases, you got exponents, you got products. This is base 5, so I'm going to make it log base 5. Remember, it's a smaller number in the lower right, I'm going to say the corner of the logarithm. And then it's log base 5 of the product. Well, the product over here is showing as 1 over 625. So I'm going to write that as 1 over 625. Now, it's okay to write it like this, and I can tell the difference between my base and my product for my logarithm. But because I'm a math nerd, I feel better with a fraction like that if I put it in parentheses. Do you have to? Not necessarily, but if this was a test and the 625 looked like it was part of your base, that can be problematic, okay? So I do recommend, if you have fractions like I have right here, use parentheses. You can use parentheses even if it's not a fraction, but you don't necessarily have to. So that's the logarithm, but it should equal the exponent, which in this case is -4. So we just make it equal to -4, and we have created a logarithm from an exponential equation. Okay, so this one, we're changing a logarithm into an exponent, right? And in this logarithm, it's important to understand the different parts, right? So right here, I see a base of 64. So my exponent will be base 64. And then the exponent is whatever the logarithm equals. In this case, it's the 1/3 there. So it's 64 to the power of 1/3. This would equal the product, which is what the log is of. And in this case, it's the 4 right there. So 64 to the power of 1/3 equals 4, and you could type this into the calculator and you would get 4. 64 to the power of 1/3 equals 4, and that's good. So we're going to evaluate this. The problem is it doesn't show what it equals, right? So I have a base and then I have a product, 8 to the power of 6. That's fine. What we don't know is what the exponent is. Now, since it's not showing an exponent, we're going to force one in there. I'm using y. You can use whatever letter you want, but I'll use y, okay? Now, this will allow me to change this into exponential form, because log base 8 of 8 to the power of 6, what the crap is that? Let's find out. But the exponent will help us because, again, logarithms are fairly new to us. And so I'm going to take my base 8. I'm going to make it base 8 to the power of, that's what the log equals, 8 to the power of y. And then this would equal, in the logarithm, what it is of is the product. Now this is showing 8 to the power of 6, so I get 8 to the power of 6. What you notice right here is that the two bases are the same. We got an exponent equals, we have a base and an exponent equals another base and an exponent. If the bases match like we see here, then we can simply compare the exponents. Okay, so it's kind of like a principle of equality here. I'm going to ignore the bases, and I'm going to rewrite this equation with just the exponents. Because if we could get the exponents to match, then it would be 8 to the same power. Well, that's an exponent of y on the left and an exponent of 6 on the right. And I can see that I don't really have to solve this any further. I just get y equals 6, and that's done. So log base 3 of 243. So I know my base, I know my product. What I don't know is the exponent. It's not even showing an exponent, so I'm going to have to actually put that in myself. I'm going to make this equal to some variable. Now we used y on that last one. I'll use x for this one because it doesn't matter. But that x right there is also the exponent, right? So I'm going to change this into exponent notation or format. And I have log base 3. That's base 3 is also the base for the exponent. So I have 3 to the power of, remember the log equals the exponent. So this is 3 to the power of x equals, and it's whatever the log is of, in this case 243. That is the product, 243. Now, I'm okay with my multiples of 3, but up to like, 3 times 12, 36, right? I don't know what I would have to multiply 3 by to get 243. The good news is that I don't necessarily have to. And also the other thing, remember, is that it's repeatedly multiplied by 3. So I'm going to go through this and just simply divide by 3. I'm going to use prime factorization. You can use a calculator if you want, if you know how to do that. But for now, I'm going to take 243, I'm going to divide it by 3, specifically because the base is 3.
3 and 81.
Yeah, 3 and 81. 81 divided by 3, 27. Okay, now I'm going to circle the 3's because that's important. 27 divided by 3 is 9er, and 9 would be 3 times 3. So it works. 243 is a product of, I guess, 3's. So I'll say that. So here's what I'm going to do. I'm going to change this. I'm going to take 3 to the power of x. 3 to the power of x equals, but instead of writing it as 243, and this goes back to what we were talking about at the beginning, if you can change things to look different, but they're more convenient for you in math, but not change the actual value, do it. So right here, this is now 3, base 3, yeah, to the power of 1, 2, 3, 4, 5. Okay, so again, the bases match. Now that the bases match, I can compare just the exponents, which is x and 5. Just keep in mind, sometimes what they'll do is they'll make this like 3 to the power of x plus 8, and you got like x plus 8 equals 5. This one we didn't have to, of course, but x should just equal 5. Now you can check, right? Remember, go back to the beginning here, say, just in your calculator, put 3 to the power of 5, rather, and just push enter, see what it is. Should be 243. Okay, so that means that log base 3 of 243 equals, again, this x right here you could replace with a 5 as well. Okay, I'm going to start this one off with a mistake. Okay, very common error that we see. It's common enough, I should say. Okay, some students right here, they say log base 3 of 9, boom, 3 to the power of 9 equals, I don't know what the crap that is. But that's what they do, and that's not going to work. Okay, so please don't just take a log and be like, it's 3 to the power of 9. That's not what it's saying. Remember, the format has changed from exponential form, but that is not 3 to the power of 9. So here, once again, it's not showing what it equals, so I'm going to make it equal something. Doesn't matter what it is. I've used x and y, so what the heck, I'll make it z, because it doesn't matter. But right here, I've got my base. I always start with the base. Base 3, and then it equals the z. The z then is the exponent here. And then this would equal the product, which in this format from the logarithm is showing as 9. Okay, so 3 to the power of something equals 9. And then, yeah, 9 splits up into 3 and 3. So it's 3 times 3. So instead of it showing this as 9, I'm going to show it as 3 to the power of 2. And I'm using exponent mode or notation on purpose. See if I can get this to work. There we go. Okay, so this is my new equation. And now that the bases match, I get to ignore them completely, meaning that I now have z equals the other exponent, 2. So once again, if you were to go back here and put 3 to the power of 2 in your calculator, push enter, you're going to get 9. And we'll show how to put this in the calculator here in a moment. As it turns out, all of those that we just did, you could put into the calculator if you wanted to. I don't know anyone that wants to, so, but hopefully it helps, okay? So if you saw something like this right here, log base b of a, again, b and a would be numbers. They have to be given right here. Meaning you have a base and you have a product. You can type this into the calculator. We just have to change the format. It's called a change of base. And so there's reasons why this happens. I also assume you don't care. But what we do is we change these into more familiar logs. Well, no logs are familiar because this is brand new for us, maybe, unless you've taken 990. And hopefully it's not new. But if it is, then these aren't very new to us. But what we have, I'm going to use a button on my calculator. It's the log button. Now, this isn't any log right here that I've just put on there. In fact, the button on the calculator that we use, it actually is a button that says log on it. But this isn't just your average log. It's a common log, which we'll get into in the next lesson. You don't have to worry about that right now. Just understand that there is a log button. So if I made an example out of this, which I assume you're already sick of this, but here we go. If I had log base, I don't know, 2 of, we'll make it, I don't know, 128. That's a nice big number. I can type this into the calculator and let the calculator do the work for me. And the calculator says, thank you for letting me do the work. So I'm going to make this a fraction now with, again, this would be common logs, both. But the product there, the 128, is always in the numerator. And then the denominator is always the base. Okay, now if I put this into the calculator, just like we see it, the calculator will solve this for me. Thank you, calculator. So here we go. In fact, I'll make it a fraction. I'm pushing the n over d. Now the log button that I'm looking for looks like this. I mean, it's not proportional, but in the top left you see the button. It says log. I'm pushing it right now. I push log. You can see right now on the calculator it says log, and then parentheses. It's saying, what do you want the log of? Well, over here I know it's 128, right? So 128, close parentheses. So I just type that in, 128, and then I close the parentheses. Now we've got to go down to the bottom. I'm going to push log again. I need to type in log 2. So I push log. It shows log, parentheses, saying, what do you want the log of? Well, 2. I'll take 2. And then I'll close the parentheses, and I push enter. And the calculator says, oh, it's 7. Okay. What this means is that 2 to the power of 7, it should equal 128. Now you can check that in your calculator. 2 to the power of 7 is 128. It does. Evaluate this. Log base 64, 4. So this one, we don't have any more information here. I need to change this into exponential form, and then I can solve or evaluate from there. Okay, now,
Did you skip something?
let's do this one twice, because this one, if we do it only once, it just won't be as much fun. So let's do it over here first. And like I said, we're going to do this one by hand first. So I'm going to take my base 64. Well, I should make it equal something, shouldn't I? So we're going to make it equal, I don't know, W, because L looks like 1. So I got my base 64, and then it's going to be the power of W, because the log always equals the exponent, and this would equal the product. For my log, it's the log of 4 there, so it's going to equal 4. Now, just so we understand, or hopefully remember, is with exponent rules, right? This is 64 to some power equals 4. It's equaling something smaller than 64, so I should expect my exponent to be something less than 1. Okay, because if once you get to 1, it's 64 to the power of 1, which is just 64. So, but I got something smaller, so I'm going to have to raise it to a power of something smaller than 1.
0.3.
Now, the problem here is that my bases don't match. If I can get my bases to match, like we've seen, I can ignore the exponents, okay? So I'm going to take this 64, and I'm going to split it up into base 4s, right? So I'm going to divide by 4. I know I can divide by 2 or 8 if I wanted to, but I want base 4s because this base right here is 4, and you could even say that that 4 has a power of 1 if you wanted to. Okay, so that'd be 4 times 16, and then 16 would be 4 and 4. So you see how that comes out very, very pretty, right? So it's now 4 to the power of 3. Okay, that was the 64, though, part of that, and that was to the power of W. And this equals 4 And right now, I'd like to see that exponent of 1 right there. The bases match. And in fact, I don't really need those parentheses, which means I could, if I wanted to, write this as 4 to the power of 3w equals 4 to the power of 1. Now, not many students show this step because hopefully we have some familiarity with some exponent rules, but if not, you can show this step. But the exponents match, right? So I can rewrite this with just the exponents. I can say, well, 3w should equal 1. We are solving for w here, the variable that we made up, so I'm going to divide both sides by 3, principle of equality. W equals 1/3 or 0.3 repeating. I like the fraction better, just because, I don't know, it's prettier, I guess. I've been boxing in the variable there, but really all we need is the 1/3. Okay, now that's doing it by hand, and that was super fun. But let's do it with a calculator as well. Okay, so let's change that base. And so we'll make this a log. Again, I'm going for the log button. You can use the natural log button if you understand what that is, but you don't necessarily have to. So it's log of 4 over the log of the base, which is 64. Okay, if you type this into the calculator, you will in fact get 1/3. And that's the value that we got as well. All right, so everything we've been doing is just what they say, usually we'll take a logarithm, we'll change it back to an exponential mode. If it looks like it helps, then that's great. But like we've seen, sometimes the calculator helps as well by changing the base. Okay, so something like this, again, just because hopefully we have a good grasp on this now, we know 5 to some power has to equal 15,625. It's humongous. But if we change this into exponent mode, maybe it'll help, right? Maybe it won't, I don't know. But it's a base 5, so I'm going to change this to exponent mode. It's 5. The logarithm equals x. It always equals the exponent, so it's 5 to the power of x. And this is going to equal the product, which in this case is 15,625. Okay, so 15,625. Now, I'm going to need this 15,625 in base 5 so that I can get the bases to match. And it should come out pretty good. And as much as you want me to do this in my head, I'm not going to. I'm going to use the calculator for this. Okay, so I'm going to take 15,625. Let's divide it by 5. Again, we're dividing it by 5 because it should be repeatedly multiplied by 5. That's the base. When I do, I get 3,125, which then I can divide that by 5. So divide that by 5, enter, and I get 625. I can divide that by 5 as well. And that would be, thank you, 125. Divide that by 5, and you get 25. And 25 is 5 to the power of 2, or 5 squared. 5 times 5. So let's rewrite this then. So now I have 5 to the power of 1, 2, 3, 4, 5, 6. 5 to the power of 6 equals 5 to the power of x. Now you'll notice that the bases have come out very nicely for us, just like they have on the other problems. That's because we're just trying to get used to bases. Is everything always going to be divisible by the same base? Perhaps not. Maybe not. Who knows? But hopefully we can use a calculator to help us solve. And now that my bases match like we've seen, I'm going to take my x and just say it equals 6. That should be good enough. And now, again, you can try. We solve for the exponent. That's what x is, the exponent. If you type into the calculator 5 to the power of 6, you should get 15,625. And now we get to feel really good about what we just did. Let's go over it still, because, we're having so much fun. So log base 6 of a equals 5, and a there is the product this time. A little bit different, right? The base is 6, so I have 6 then. The log equals 5, so that would be our exponent, 6 to the power of 5 equals a. Now, sometimes, just because this is new, students look at this and they're like, what am I going to do now? Well, just put in the calculator 6 to the power of 5, and that's when I got in the calculator, 7,776, and then you're done, okay? Because, again, sometimes we may overcomplicate this at this point, and we're expecting a little bit more, but no, just 6 to the power of 5, type that in to your calculator, be done with it. Or do it by hand. But you should get the same answer. if we do not like using factoring to solve logarithms for the exponent value, we can change the base property for logarithms. Again, this is what we've seen already. But we're using those common logs right now. You can use natural logs if you want, but we haven't gone over those. So we're going to stick with logs because hopefully the button at least looks a little familiar. So yeah, if we see something like this, we can just rewrite it as a log. Well, we're not showing the logs when these say. So this is showing log base C. The button we're using in the calculator is just a regular log button. So it should look just kind of like this. By the way, there is a base for these common logs that I'm using. We just don't care about that right now because it's not in the list. There is a base for that log. We just don't care about it right now. Yeah. Okay, this one, let's just type it into the calculator, see what we get, okay? So once again, it's going to give us that fraction. And since we're using just the log button, it shouldn't be log in the numerator and denominator. Log of what? Well, it's always log of, see if we got parentheses right there, log of the product first, so log of 1 over 64. I'll keep that in parentheses, what the heck. And then it's, the base is 4, so it's always the log of the base in the denominator here. Okay, so, yeah, excuse me, if I put this into the calculator, we should get an exponent that would have been -3. You could check, right? Type 4 to the power of -3. What do you get? Should get 1 over 64. If it gives you the decimal, just push the double arrow button, and it'll change that into 1 over 64 for you. All right, now we got to be able to graph these suckers. We'll have to remember which one's the x, right? You see how right here the product is the x? So if by chance you change this into exponent mode, you got your base, and then f of x, I'm just going to use y for that. So you'd have b to the power of y equals x. I have that backwards because it's the exponent there. But log base b of x, yeah, it should equal the x right there. Okay, so x is the product. Do you need to do that? I don't know. I mean, we're going to, but the reason why we're going to do this is usually it's going to make things easier, which also means that for these logarithmic functions, we need to choose a y value, not an x value, which may go a little bit backwards from what we're used to. Now, if you're familiar with exponential graphs, which I believe we've done in this class, not just the parabolas, but just regular exponential graphs, they usually look kind of like this one. This is an inverse of that because, again, the x and the y have kind of been switched spots on this. Okay, so we usually end up with a graph that maybe looks something like this, or maybe one that looks like this. You can see right here, this is just saying if b is some kind of fractional or decimal value less than 1, then we should end up with some kind of fraction like this. As long as the b is greater than 1, though, then we should end up with something that looks like this. Of course, if the b is 1, then it'd be a straight line, but we don't give a crap about that. The y-intercept here is 1, 0. It doesn't always have to be. There isn't typically a y-intercept because it typically does not go through the y-axis. The domain, so notice 0 is not included here because we got parentheses, but anything to the right of the y-axis would work. And then the range, it goes infinitely upwards and then infinitely downwards for both graphs as well. Just little characteristics of logarithms. Really, we're mainly concerned with this, just being able to change the logarithm into exponential mode, and then we choose y values for ourselves. But again, once we get those, then we're looking to make a table on our own that, well, again, we're choosing those y values. We want to choose y values that are easy, y values like 0 or 1. You can try -1, but it should be out of the domain, or 2 or 3, something like that. Y values, and then you find the corresponding x value to get your ordered pair. Okay, so let's take this log. It says g of x. Remember, it doesn't really matter what the function looks like. In fact, let's show the log as just y equals instead. So it's log, y equals log base 5 of x. Okay, so I got a base 5. And I'm just changing this into its exponential mode. So I'd have 5 to the power of log equals y there. So that's going to be my exponent, y. And then it would equal the product, which again, in this case, it's going to be x. Okay, so when we find values to use, we have to choose values of y because it's going to be a lot easier than choosing values of x in this case. Right, 5 to the power, like if you said x equals 1, 5 to the power of what equals 1? I don't know. I couldn't even tell you. So maybe if I thought about it, but I don't care. I do care. I need to not go there. So again, I'm choosing y values, right? Let's choose, let's just, I don't know, just be a smart aleck. Let's say y equals -1. That's going to work, actually. That's pretty nice. Well, that would be 5 to the power of -1 equals x. Well, 5 to the power of -1 is just 1/5 equals x. You can make that 0.2 if you'd like. Okay, we can fit that on the graph. So x equals 0.2 and y equals -1. Oh, geez. It's, about right there. Sorry if that doesn't show up very well. Okay, so -1 gives us a fractional value, a decimal value. In fact, if we wanted to take this to the limit, well, not really the limit, but if you said -2, y equals -2 right here, then you'd get 5 to the power of -2 equals x. So that'd be 1/25, which is very small. I don't know, maybe 0, be less than that. 1 divided by 25. 0.04. Now, this graph is small enough, I can't really get to the hundredths on that, but, something like that right there. And it's just like we saw with the characteristics, right? This graph is going to get very, very, very close to the y-axis, but it should never actually get there or cross it. So I'm going to stop there. I just know that this line is going to get really close to the y-axis. So let's see what happens when we go in the other direction. Let's make y 0. Okay, so that'd be 5 to the power of 0 equals x. Anything to the power of 0 is 1, so 1 equals x right here. So I get 1, 0. That is an x-intercept right there. Got that on the graph. Now let's go up from there. So we'll say y equals 1. That's nice. 5 to the power of 1 equals x. Well, that's just 5 equals x. That's pretty good. So I get the ordered pair of 5, 1. Let's put that on the graph. 5, 1. Boom. That's the last one I'm going to be able to fit, because if I make y 2, then I've got 5 to the power of 2, which is equal to x. So 25 would equal x. No, it's too far. It's way over here to the right, way off the graph here. But that's enough of a pattern right there for me to draw, because it's, again, if you were to try more negative values here, you'd get something even closer and closer to 0 as you tried lesser negatives, I guess. Okay, now let's see if I can draw this. That's where I'm going to struggle. Try not to suck so bad at drawing like I do. Oh, it wasn't too bad for that part. All right, here comes the little bits at a time. Going to try to get close to that, trying to hug that y-axis right there, but not get too close to it. That's not too bad. I'll take that. So there's my graph. All right, let's change this one into y equals instead of function notation. So y equals the negative log base 3 of x. Okay. Now, yeah, some people say, well, I got my base 3. That's nice. And we got our product x. In fact, we have our exponent y. The problem is that this negative in the front is throwing things off. What the crap do we do with that negative right there? I would treat this as -1. And I don't like that there either, right? So I would probably get rid of it. So let's get rid of that. How are we going to get rid of it? I'm going to divide both sides by -1. Okay, so that's going to make that a phantom 1. I should have moved this, but now I have log base 3 of x, right? Because we got rid of that negative. It's a phantom 1 that's right there. I just don't want to see it there. But now I've got y divided by -1. As it turns out, that just makes it -y. You can say -1y if you'd really like, but it's not really going to make a difference. Yeah, whatever. -y. Okay. Well, this is good enough to write in exponential form. So let's change this into exponential mode. So I do have a base. That's a very nice base of 3. I have an exponent. That's what log equals, right? The -y. It's okay that is negative, by the way. And then this would equal the product, and it was a log of x, so it's going to just equal x right here. So this is my exponential function. It's the same function that we had in the beginning. But at this point, I'm going to make a table. I'll do it on the left. I'm going to give myself a nice table, and then I'm going to choose values of y, and then I should have corresponding x values. Now, I'm putting a lot of lines in here. Are we going to use all of them? I don't know. I also don't care, because if we don't use them, that's fine too. Now, on that last problem, we started with negatives. You can start with positives if you want. Some students like to start with 0. And I like to start with 0 too, because 0 is a nice value to work with. So that would be, yeah, it's going to be 3 to the power of -0 equals x. Well, anything to 0 can be positive or negative, right? But anything to the power of 0 is 1, so just x equals 1, okay? Now that's an ordered pair we can put on the graph. We got 1, 0, right? So let's not do that. 1, 0. Boom, found it right there. Now you can go up or down at this point. You can make your y's more positive, maybe more negative if you like. It doesn't matter. I'll go in the positive direction. What the heck? Okay, so that's a y value that's 1. Okay, so again, this would be 3 to the power of -1 equals x, which is really 1/3 equals x. That's really just 0.3 repeating. But since I can't get hundredths on my graph, I'll just keep this in the tenths. In fact, the tenths is going to be hard enough. But yeah, let's try to put that on the graph. So 0.3 and 1. 0.3, about right there. We'll see. We'll pretend like I'm doing this extraordinarily well. Let's try 2 then. So that'd be 3 to the power of -2. Again, that's going to equal x. So that'd be 1/9 equals x, which is 0.1. So that's just, I can get really close to that y-axis right there, but it's just going to get closer and closer, okay? So the next one would be 1/27, I think. Yeah, 1/27. 1/27, 3. Again, 1/27 is just, it's going to get really close to 0. That's on purpose. That goes back to exponential form stuff, which I don't really want to cover right now, okay? It's called an asymptote if you care. It's not something I would use on the street, because if you call someone an asymptote, that may not go over very well, but maybe you like it, maybe you don't. I think we covered asymptotes, whatever. Okay, so that's if I were to take the values of y and make them more positive, right? But let's make them more negative. So if I said over here that y equals -1, then I'd have 3 to the power of -1. Well, that's 3 to the power of 1. This equals x, by the way, which is just 3. Well, that's a nice value to put on the graph. 3, -1, which would be right here. Okay, well, what the heck happens then if I make this y -2? So that'd be 3 to the power of -2. It's going to equal x. That's really just 3 to the power of 2 equals x. That's 9. So that's nice. I can put that on the graph too. 9, -2, found it. It's right there. All right, now comes the hard part when you're doing it by hand. Let's get this on the graph. All right, so this part, yeah, I like to do little parts at a time. Maybe it looks a little sloppy, but I don't give a crap. Well, maybe that one's more sloppy than I'd like it, but I'll keep it. And then, it's got to go, get really close to that y-axis right there. Not actually touch it. I got to take this to the edge. And I'll put the arrow on. There we go. That's it. It looks pretty good. If you're doing this by hand, put as many points on the graph as you can. Now you notice I'm not putting these points on the graph. Well, why aren't you doing that? It's because I know it's get really close to this y-axis. But why am I not doing y equals -3 in the table either? Because then I'm going to get 27, and then it's off the graph. But I know I can get -2.9 on the graph. Just double check. And by the way, you can put this in the calculator and see what it gives you in both x and y values there. So This one, let's move this over here so we have a little bit more space to work with. So on this one, let's change it into exponential form. Well, actually, first let's change it into y equals, right? So instead of h of x, we'll make it y equals log base 4 of x minus 3. Okay, so now that we have it like this, it's just easier to do it, change this into exponential mode notation from here, because not everyone wants to see 4 to the power of h of x. So if you can, though, that's fine. But that's base 4, my exponent's y, so 4 to the power of y equals the product, which it shows right here was x minus 3. Now, you can keep that in parentheses if you'd like, but you don't necessarily have to, and I'm not going to because it's going to add stuff that I have to write. So I got 4 to the power of y equals x minus 3. I don't really like this x minus 3 business because I'm choosing y values in the table. So I'm going to get rid of that minus 3 with the principle of equality. So let's add 3 to both sides. Okay, so that it ends up being 4 to the power of y plus 3 equals x. Now, I feel a lot more comfortable choosing my y values, even if I end up with some decimal values. Okay, so let's get together a table here. I got x's and y's, something like that. And let's find some values to put in the table. Now, again, I am choosing y values because it's 4 to the power of y equals 4 to the power of y plus 3 equals x. And back here, even if you're like, I can now start choosing values of x, you could. Again, I just don't know how you can do that with the 4 to the power of something equals something else, unless it actually is something that has a base 4. So now that I have this, let's start choosing some values that are nice to work with, like 0. So that would be 4 to the power of 0 plus 3 equals x, which is really just 1 plus 3 equals x, and 1 plus 3 is 4. So I now have an ordered pair of 4, 0. That's a x-intercept right there. Found it. Okay, let's take this up. Let's go up by 1 here. All right, so this would be 4 to the power of 1 plus 3 equals x, which again is just 4 plus 3 equals x, which is 7. So now I've got an ordered pair of 7, 1 right there. Okay, let's try 2 then. 4 to the power of 2 plus 3 equals x. That's 16 plus 3 equals x. 16 plus 3 is 19. Yep, it's already off the graph. So that means that as you go to the right here, it's getting steeper, well, I guess more shallow, but more level as you go to the right here. No problem. Because now I can go backwards on my y's. So I'm going to make y negative 1. So what does this do? I got 4 to the power of negative 1 plus 3 equals x. That'd be, well, 1/4 plus 3 equals x, which is 3.25. Now, it's going to be kind of hard to graph that, but here we go. So 3.25, negative 1. About right there. Okay, well, let's try y is negative 2. It's going to be even uglier. This, what the heck? 15, 3. About. Yeah, so again, I'll show the work here. So that'd be 4 to the power of negative 2 plus 3 equals x, which is 1/16 plus 3 equals x. When I put that in the calculator, it gave me 3.06 or 3.1, right? Now that value is already very, very, very close to an x value that's 3. And that means that if you were to put more negative y values in here, you're going to get something even closer to 3 as we go. Why is that? It's because back here with the exponential format right there, the plus 3, that becomes an asymptote. Okay, so again, that means that we'll get really close to 3 because we can make this really, really close to 0. So we get something really close to 3. It just doesn't actually end up being 3. So that means that these dots are going to get really close to 3 as we go down this line right here. And now we can kind of see how this is going to work with the graph. So let's see if I can put this on the graph here. Yeah, it wasn't too bad. And then, like I said, we got to get this really close to x equals 3.
Why is 3 the isaac code again? Yeah, here. So
In exponential notation, if you have anything added or subtracted with something that's just base to the power of y like this, something added to it, that becomes your asymptote.